Hi young engineers, good morning, happy Thursday. Things will always be sweet if you keep working. This morning we will learn about Newtonian fluids. Newtonian fluids can be defined as fluids in which shear stress is directly proportional to rate of deformation. This definition starts from a viscous flow. Consider the viscous flow in this pipe. In viscous flow there are like layers of fluid. The further from the pipe wall, the faster the speed of the fluid layer. Of course, the fluid layer in the middle of the pipe will move the fastest. We will analyze the fluid layer that is right above the pipe wall. In this fluid layer there are two lines. The bottom line can be said to be the pipe wall. When this fluid moves, the top line shifts to the right. The object moves because of a force. Because the top line moves to the right, we can assume that there is a force pushing the layer to the right. We have known the concept of shear stress before. Place this fluid layer into a three-dimensional Cartesian coordinate system. It is clearly seen that the force F acts on the top line of the fluid to the positive x-axis, while the normal direction of the upper area of the fluid is to the positive y-axis. So this fluid experiences a shear stress of tau yx. Now, let's look at this fluid from the front. We can draw an angle of theta. When the force pushes to the right, the angle theta also changes. The change in the magnitude of theta with respect to time is the deformation rate. Well, a fluid is said to be a Newtonian fluid when the magnitude of the shear stress is proportional to the deformation rate. In a fluid that moves continuously, the empty part will be immediately filled by the previous fluid. We will have difficulty measuring the value of this theta, let alone the change of theta with time. Therefore, we need to define the deformation rate as a physical quantity that can be easily measured. Suppose the top line moves at a speed of du to the right, the top layer has shifted as far as dx. The definition of linear velocity says that du is equal to dx dt. At the same time, the angle formed is d theta. Based on the concept of tangent, tangent d theta is equal to dx dy. Because the thickness of the fluid layer is dy. For small angles theta, tangent d theta is equal to d theta. So, d theta is equal to dx dy. Both values of dx are the same physical quantity. We can compare the two equations for dx. Du times dt is equal to d theta times dy. From here, d theta dt is equal to du dy. Now, we can use the value of du dy instead of d theta dt in the previous equation. Tau yx is proportional to du dy. The proportionality will turn into an equation by multiplying one side by a constant. This constant is known as the viscosity, mu. So a fluid can be said to be a Newtonian fluid if tau yx is equal to mu du dy. We will use this equation often in the next series. Happy learning, everyone.
Yeah, I'm about to fade away, cause every time I wake up I feel like it's Monday. Something's going wrong with all the chemicals up in my brain. All of a sudden I don't look at anything the same way. Gotta build up of my thoughts sitting in an ashtray.